In this video, we're going to focus on what's called trig substitution. These do not actually start out as trig integrals. And in fact, it's a trig substitution that allows us to solve it. It starts out algebraic, possibly with radicals, often with radicals, but basically it's something that looks like it's using the Pythagorean theorem, something squared plus or minus something else that's being squared. Now, keep in mind that a constant can always be thought of as something being squared, because if you think of the number 5, you can think of it as, well, the square root of 5 squared, and that's 5. So we're looking for something with a variable in it being squared plus or minus some constant being squared, or reverse the order, where you have the constant thing being squared minus something with a variable in it being squared. We're going to do a trig substitution, which will let us convert what was an algebraic integrand into something involving trig. And then we'll be able to convert from a definite or an independent variable of x into an independent variable of theta. So we're converting from the original algebraic with x into something with trig and theta instead. And then we'll undo the process, and we'll undo the process using the Pythagorean theorem and also the triangle that we draw from right triangle trigonometry. We'll also probably have to use inverse trig functions. So this might be a good opportunity for you to go brush up on your inverse trig integrals and make sure that you remember what their derivatives are and how to work with inverse trig. And make sure that you're familiar with them before you get started on the homework in this section. Now, these are probably among the more difficult problem types that we'll be solving in this chapter, not necessarily because they're so difficult in themselves. Well, they are difficult, but mostly they're complicated, right? There's a lot of moving pieces, and you have to remember to convert each piece. The real problem is that after you've converted them into something with trig and the independent variable being theta, you may end up with a trig integral, as we saw in the previous two videos. So not only do you have to do a trig substitution, but you may have to do some trig integrals themselves as part of the trig substitution. That can make these very, very long problems. And by the time you reach the end, you've kind of forgotten where you started. So you want to make sure you're not too tired when you do these problems so that you don't make a lot of careless mistakes. Let me share my screen with you, and then we'll get started looking at what some of the patterns are that we need to work with. You should now be focused on my lecture notes for this section. What we want to do is we want to convert something that looks like something with the variable squared plus or minus some constant, or some constant plus or minus something with the variable squared. That just reeks of the Pythagorean theorem, which of course is the key to solving these particular ones. So how do you know that you need trig substitution? Well, the integrands are primarily algebraic in nature, but again, the form of it is reminiscent of the Pythagorean theorem. And then we'll be able to use right triangle trigonometry and the definitions of the trig functions in order to make good substitutions that will let us solve them as integrals of something involving theta. So we're looking for something squared plus or minus something else being squared, where one of the somethings has the variable in it, the independent variable, which is usually x. So when we're starting, a lot of times it's in the denominator of the integrand, and the denominator of a fraction. It may or may not be under a radical as well, but not always. Sometimes it's not in the denominator, sometimes it's not under a radical. But it always does have this pattern that can be written as something squared plus or minus something else squared. And again, this reminds us of the Pythagorean theorem. Now, remember, like I said before, that all constants can be thought of as something squared. You just take the square root of it and square it, and that makes it into a perfect square, even if it's not a perfect square. So what's the simplest case that we can look at here? We'll look at first x by itself, and then we'll look at a more generic function of x rather than just x by itself. if x is being squared and the other thing being squared is some kind of constant, this is as simple as it gets. Not simple, but as simple as it gets. So we either have a constant squared minus x squared, or x squared minus the constant squared, or they're added together, x squared plus a constant squared. Okay, now when we look at these remind us of certain identities coming from the Pythagorean trig identities. So let's scroll down and look at these. These are coming from the first two. So the first in here, we see this constant minus variable thing is more reminiscent of 1 minus sine squared of theta. 1 being a constant and sine of theta having the variable theta in it to correspond with this being x. So we've got the variables in the second part. And then x squared plus c squared kind of reminds us of tangent squared of theta plus 1, which gives us secant squared, of course. And so again, we're matching the variable parts on the left and the constant parts on the right. Now, the third one is the more tricky one when we integrate. It's the one that occasionally, in certain cases, might have a negative on it. It's rare that it happens. It almost has to be a definite integral for us to be able to evaluate, because we have to know whether x is larger than or equal to c, or if x is less than or equal to negative c, which we won't know unless we know something about x, which means we have to have a definite integral. We'll assume for the most part that it comes out positive, and you'll see in just a second what I mean. So this would be more like secant squared of theta minus 1. So we're looking at these, and you can see that I'm making a substitution here, that this constant squared is going to correspond to the 1, and this variable x squared is going to correspond to the trig function being squared. Now, if that's the case, we can make what's called a substitution. And the substitution is going to be x, the variable thing being squared, is going to be equal to the constant, not the constant squared, but the constant times the trig function, not the trig function squared, but the trig function. So x equals c sine theta, or in the middle, x equals c tangent theta, and on the right, x equals c secant theta. Now, this isn't going to make any sense to you at all until we get actually to doing some of these and you see how it works out. Now, I have no idea how long it took somebody to come up with this, but my guess is months and months and months, if not longer. This is a very difficult, involved process. They also had to make some decisions about the angle theta because they're using inverse trig. So remember that inverse trig only uses 2 quadrants at a time to define it. Since we're using sine here, they use the same range for theta that we use in inverse trig. So this is going to be between negative pi over 2 and pi over 2. Now this turns out to be important because 1 minus sine squared of theta can be replaced with cosine squared of theta. If we take the square root of cosine squared of theta, we get the absolute value of cosine theta, but cosine is positive in both of these quadrants. So the absolute value is equal to cosine, and that lets us drop the absolute values. In the second case right here, because we're substituting with tangent of theta, we again use the range for tangent of theta, which is negative pi over 2 to pi over 2, and we have a similar thing going on. We have secant squared of theta plus 1, which can be replaced with, or rather tangent squared of theta plus 1, which can be replaced with secant squared of theta. And if we have that under a radical, the square root of secant squared is the absolute value of secant. But if we're only talking about quadrants 4 and 1, secant's positive in both, so the absolute value is equal to secant of theta. The only one that's difficult is this third one over here. When we use this substitution where x is c secant of theta, we get secant squared of theta minus 1, which can be replaced with tangent squared of theta. Now, secants, 2 quadrants for the inverse trig function are quadrant 1 up to pi over 2, but not including, and between pi over 2 and pi, so quadrants 1 and 2. Now we have a problem because tangent is positive in quadrant 1, sure enough. So the square root of tangent squared is the absolute value of tangent, which is tangent. But if it's in quadrant 2, it would give us a negative tangent. So this is the one case in a definite integral where you have to think about where you are on the unit circle. So now, how does this relate to the triangle and right triangle trigonometry? So let's scroll down a little bit and take a look at this now. So we have these substitutions that we're going to make for each one of these different types. We have a squared minus x squared right here, a squared minus x squared, which is 1 minus sine squared, x equals c sine of theta. But if x is equal to c sine of theta, then I should be able to solve this for the sine of theta. So this tells me that sine of theta is equal to x divided by c. And then I can come down here and I can draw a right triangle where in fact the sine of the angle is x over c. Remember, sine is opposite over hypotenuse. So if these two sides are set, then because this is a right triangle, and I really should have a right angle down here in the lower right corner, then I can use the Pythagorean theorem to get the third side, which is the square root of c squared minus x squared. But that's where this started, right? Remember that we were substituting c squared minus x squared in the very beginning. So in essence, what we have then is a relationship between the two through the right triangle trigonometry. We can do the same thing in this next one right here. This was x squared plus c squared. So let me put that up above here so we can see it. This is x squared plus c squared minus x squared, and x squared minus c squared. So when I look at this one, this reminds us of the Pythagorean identity part, tangent squared of theta plus 1. When I make a substitution, I let x be c tangent of theta, which means that I can solve it for tangent of theta, which becomes x over c. So that's opposite over adjacent. When I draw the triangle down here using right triangle trigonometry, again, that's a right angle there and there, then I have x over c. And then I can use the Pythagorean theorem to find this side. Notice that this corresponds to what I had up here in the beginning. And that's not a mistake. That's always going to occur. Whatever you get under here is going to match what you started with. If it doesn't, we've made a mistake somewhere. The last one, of course, is secant squared of theta minus 1. It's the more difficult one because it's got the case where tangent of theta absolute value is not equal to tangent of theta if x is less than or equal to negative c, which we won't know unless we know something about x, which pretty much requires that we have a definite integral. So when we make this substitution, we do x equals c secant of theta, which lets us solve for secant of theta, and secant of theta becomes x divided by c. Now, secant of theta, of course, is the reciprocal of cosine. Cosine is adjacent over hypotenuse, so secant is hypotenuse over adjacent. So we get hypotenuse over adjacent, and then we use the Pythagorean identity to come up with the third side. But this third side, of course, corresponds to where we started from. So we see this relationship going on between the three parts. Now, what are we going to do in order to build the rest of this? Well, one of the things that we do is, since we started on the far left one with c squared minus x squared, and then we made a substitution that x equals c sine theta for this first one, then we can replace the x with c sine theta, and we get c squared sine squared of theta. Well, the c squareds are common factors in these two terms, so we can factor it out, and that gives us the 1 minus sine squared that we had in the original that we said it reminded us of. So we're basically forcing the square peg into a round hole, and 1 minus sine squared gives us cosine squared. So we've reduced this c squared minus x squared, which started out algebraic, had nothing to do with trig, into something related to trig. And instead of having x for the variable, now we have theta. So same thing happens in the second two parts. In the second two parts, we're making a different substitution. In this one right here, we're letting x be c tangent of theta. So when we do the substitution into the original x squared plus c squared, we get c squared tangent squared plus c squared. Factor out the common factor of c squared. Tangent squared plus 1 is a Pythagorean identity, gives you secant squared of theta. Notice that one of the things that we're doing is converting from something relating to x to something relating to theta. And another thing that we're doing is converting from something that has two terms in it into something that only has one term in it, no addition or subtraction. This is important when these show up under radicals, because if I go from two terms to one term, I should be able to take the square root. Now, the last one, we make the substitution over here that x is equal to c secant of theta. And when we do that substitution, we end up with x squared minus c squared becoming c squared secant squared of theta minus c squared. Take out the common factor of c squared, and you get c squared times tangent squared of theta. That's the one that has a little bit of a problem if x is less than or equal to negative c, which again, we won't know unless we know something about where x is being evaluated. Now, because of the way that the angles are defined, the first one, the absolute value of cosine, becomes just cosine. And the second one, the absolute value of secant, becomes secant because these are both in quadrants 4 and 1. 4 going backwards, 1 going forwards. This one, however, is in quadrant 1 and quadrant 2, and that's a problem because this is tangent of theta. And so the absolute value of tangent of theta is only tangent of theta if x is greater than or equal to c. Otherwise, you would get a negative tangent of theta. Okay, now you're probably looking at all of this going, this looks completely Greek to me, and I have no idea what you're doing. I can't figure it out. It's too much information. All right, well, we're going to have to do a little bit more information, and then we're going to get started on actually working an example. And I think once we start the examples, you'll see how it goes. So what have we done? We've switched from x being the variable to theta being the variable. But this was an integral, so we had a differential, and our original differential was dx. If I switch the independent variable from x to theta, then I have to switch the differential from dx to d theta. So I go back to the original substitution that I made, and here are our 3 substitutions for the 3 different types of trig substitution problems. And I compute what the derivative of it is with respect to theta. So what I'm really doing is I'm taking the derivative with respect to theta of the left side and the derivative with respect to theta of the right side. So I'm taking the derivative of both sides with respect to theta. Now dx d theta would be here. And since the right side is a function of theta, then this would just give me c cosine of theta. So then I would have dx d theta is equal to c cosine of theta. Now, once I have that, I need to solve for dx, because remember, I switched the variable from x to theta, which means I have to switch the differential from dx to d theta. So I solve for dx by abusing the notation and swinging the d theta around. So that gives me that dx is c cosine theta d theta. In the middle part, I do a similar thing. I take the derivative with respect to theta of both sides, and this would give me c secant squared of theta with the d theta slid around to the right side in the abuse of notation. On the third substitution, I get dx equals c secant of theta tangent of theta d theta. So these are the 3 that we have to worry about, the 3 different types of trig substitution. Remember, you're converting using this substitution factor in each individual one to convert from an integrand focused on x to an integrand focused on theta. And then you have to switch the differential from dx to d theta. In other words, you're going to have to substitute at least twice, if not more. Sometimes you have more factors in the integrand, which will have to be substituted out as well. All right. Now, what if the something squared plus the something else squared isn't just x? What if it is an expression involving x? So it's not just a simple x. So in other words, instead of a squared minus x squared, I have a squared minus u squared, where u itself is a function of x. So it could be 2x, or it could be x plus 3. It's some expression involving x. Well, in that case, we're going to let u be the something with x, and we're going to let a squared still be the constant part. So a is constant, a squared is constant. U has the variable x in it, but it's a function of x. So we have three possibilities. Again, same three as last time. The constant minus the variable thing squared plus the constant thing squared, and the variable thing squared minus the constant thing squared. Same thing we saw last time. Then this reminds us of the same three trig Pythagorean identities, and we'll make the same substitutions, but instead of substituting for x, we'll be substituting for u. Since this is no longer x squared and it's u squared, this becomes u. So if u is 2x, then this is 2x equals a sine theta, or 2x equals a tangent of theta. Now remember that this is a and this is a squared, so we'll have to take the square root of this to get a, right? We have the same relationship on the angles, so we're going to have the same issue with that third one that we had before. Now this is what our triangles are going to look like. When you come down here and look at the triangles, you're going to have these different relationships that you have going on here. On this first one, you have x equals a sine of theta, which means that sine of theta is equal to x over a. And when you look at the triangle, and again, this shouldn't be x, this should be u, since we're using u now. And so I get u over a, and that's what you see in the triangle right here. And then in the second one right here, we're letting u equal a tangent of theta. And so tangent of theta is u over a, and that's opposite over adjacent. And then you use the Pythagorean theorem to get the third side, which should relate to where it came from, all right? And then the last one, of course, is that u is equal to a secant of theta. And then solving for secant of theta, we have secant of theta is u over a. Secant of theta is going to be hypotenuse over adjacent. And so we get what you see here in this particular image. Now we have to build back what we had in the integral. We've made a substitution. We found the value of a and the value of u. Now we have to build back what was in the original integrand, the a squared minus u squared, or the u squared plus a squared, or the u squared minus a squared part. So we start back over with those definitions, and we use our substitution factors right here to replace u squared. This will give us a common factor of a squared, which factors out and gives us cosine squared. So we've gone from something in terms of x to something in terms of theta, and from two terms to one term. And you'll see that happening in all three cases. Again, because we have switched the variable, the independent variable from x to theta, we are going to have to switch the differential from dx to d theta. So when we're looking at this, we have u equals a sine of theta. But remember that u is itself a function of x. So it's like 2x or 2x plus 4 or x squared plus 5x plus 3. And so we can take the derivative of it with respect to theta and then swing the d theta over to the right-hand side. So we're going to take the derivative of both sides with respect to theta, and then we'll solve for the dx that's going to come out of taking the derivative of the u side. Because u depends on x, we'll get some dx there on that left side. In other words, we're going to have to do the substitution at least twice. Once for the integrand itself and once for the differential. There may be other factors in the original integrand that have to be substituted out as well. All right, in all cases, we want to make sure that the something with x that's being squared has a coefficient of 1. If it has something else, then we'll need to factor that out before creating the substitution. So we're going to look now at the different types of trig substitution, and we're going to work through 6 examples. Now, these are not what I would call simple examples. I didn't choose the easiest ones I could have. I chose some that were actually kind of challenging to kind of remind you of what trig integration is. Yes, trig integration, not trig substitution, which is what we're doing now. Because often when you do a trig substitution problem, what we're learning now, you end up with a trig integral. So you have to do both in the same problem. So let's take a look at this integral that we see right here in example 1. We have the integral of the square root of 1 minus 4x squared dx. So we've got a constant 1 minus something with the variable and it's squared, all right? So this is going to remind us basically of a squared minus u squared, which is like 1 minus sine squared of theta. This is the substitution factor that we're looking for. That's kind of the pattern that we're looking to find. Okay, so what do we want to do with this? Well, I need to figure out what a is and I need to figure out what u is. So when I look at this pattern and I try to make it match the square root of a squared minus u squared, I have that a squared equals 1. And so a equals 1. U squared, on the other hand, is 4x squared. Notice it doesn't include the negative because the negative is a part of the formula. So it's just the 4x squared that's u squared. Now we choose u to be the positive root, which is going to be 2x, right? So we have our u and we have our a. Now we want to make a substitution. What was the substitution that we wanted to make? The substitution we wanted to make was u equals a sine of theta. So u is 2x, a is 1 times sine of theta, right? So this is what we're going to do and what we're going to use. This is our basic substitution expression that we're basing this on. So 2x equals sine of theta. Now we need to do 2 things. We need to rebuild the original integrand, but in terms of theta instead of x. And we need to switch the differential from dx to d theta. So we'll do these in 2 parts. So the first thing we're going to do is we're going to rebuild the original integrand, which is 1 minus 4x squared. Now that's under the radical, so I have to remember to put it under the radical when I put it back in the integrand. But I can start with the expression 1 minus 4x squared. Well, 4x squared is u squared. So this becomes 1 minus u squared, but u squared is equal to a sine of theta. All right, well, u is 2x, right? So I have a 2x being squared. Oops, got too many bars there. And then I can replace the 2x with sine of theta. And that gives me 1 minus sine squared of theta. And 1 minus sine squared of theta, of course, is going to be cosine squared of theta. So now I have switched the expression that was under the radical from being something in terms of x to something in terms of theta, and from 2 terms to 1 term. So that's half of what we have to do, or rather it's a third of what we have to do. The next thing we need to do is we need to change the differential. So we go back to our original substitution expression, which is this guy right here, 2x equals sine theta. So I'm going to put this one in a box because it is the single most important expression or equation in the entire problem. We'll come back to it repeatedly. So now I want to take this one and I want to replace the differential dx with something in terms of d theta. So I take the derivative of the left side with respect to theta, and I take the derivative of the right side with respect to theta. Now, the derivative of sine theta is easy. That's just cosine theta. And the derivative of 2x with respect to theta is going to be 2 with a d theta on it. So this is going to give me, basically, the derivative of 2x is 2 with the d theta on it. And then I'm going to swing this around to the other side. So I get 2 dx d theta, right? The 2 is a constant, so it comes out. And I have dx d theta. Then I abuse the notation, and I swing the d theta to the other side. So I get 2 dx equals cosine of theta d theta. And then I want dx, because that's what's in the original integrand right here. I need to replace that, so I divide both sides by 2. So I get dx equals 1/2 the cosine of theta d theta. So now I have something to replace the 1 minus 4x squared under the radical and something to replace the differential dx. This is the substitution coming in. So I'm going to substitute these two pieces in place of what they represent in the original integrand. If there were another factor, there's not here, but if there were, I would also need to substitute out for it, again using this equation right here, which is our basic substitution expression. So now what we have is we have the integral of the square root of 1 minus 4x squared dx, which is equal to the integral of the square root of cosine squared of theta times 1/2 cosine theta d theta. Now remember that when we take the square root of something squared, we don't get the something. I know you want it to be the something, but it's not. It's the absolute value of it. But because of the way we define the angle in quadrant 4 and 1, cosine is going to be positive no matter what. So we get the integral of the absolute value of cosine of theta. Let's move our 1/2 out to the front. And then we have a cosine of theta d theta. And this can become, because we know that it is going to be in quadrants 4 and 1, where cosine is always positive, this is going to give me the integral of cosine squared of theta d theta. Now, how do I integrate that? Well, that's a trig integral. So you'll have to remember what we did in the previous 2 videos. We'll have to go back to evaluating the trig integral using the double angle, half angle formula. So this is going to give us 1/2 for this 1/2 times another 1/2 for the formula, the integral of 1 plus the cosine of double the angle, so double theta becomes 2 theta, d theta. Now this is going to give us a 1/4 the integral of d theta plus 1/4 the integral of cosine of 2 theta d theta. Now I won't go through all the steps, but go ahead and pause the video so that you can work it out, and then turn the video back on and we'll compare answers. How'd you do? So we have this integral right here. We do the u substitution. This is not the same u from the beginning of the problem. This is a totally different u. You can use a different letter if you want to, a different variable. Sometimes omega is good to use. Looks like a W. But as long as you don't confuse yourself, you can just use u again. And we end up with the expression 1/4 theta plus 1/8 sine of 2 theta plus c. Looks good, right? Wrong. The problem is the original integral, what we started trying to evaluate, was the integral of the square root of 1 minus 4x squared dx. That's what we're trying to find, the integral of 1 minus 4x squared dx. The problem is the original integral is in terms of the independent variable x, and my expression is now in terms of the independent variable of theta. This won't work. I've got to get back to x. So how do I get back to x? I'm going to come back up here to my substitution factor. 2x equals 1 sine of theta. So I'm going to come down here. I'm going to write it again. 2x equals 1 sine of theta. I'll box it up so that we know it's our substitution factor. So this basically tells me that sine of theta is equal to 2x divided by 1. Well, then I can draw a right triangle over here with theta being the angle in the lower left corner. And if the sine is 2x over 1, that's opposite 2x over hypotenuse 1. Now I can use the Pythagorean theorem to find this third side, which is the adjacent side. Pythagorean theorem, a squared plus b squared equals c squared, or this would be the square root of the hypotenuse squared minus the other short leg squared, which is going to give me the square root of 1 minus 4x squared. Hello, that's what I started with, way up here. Okay, good. So now I can see I've got x's back in my problem. So I'm going to come up here to this expression, and I'm going to use the right triangle trigonometry to replace the theta and the sine of 2 theta. Now, this one gets pretty tricky. It's not straightforward. This is not one of the easier ones. So first off, if 2x equals sine of theta, what's theta? Well, theta would then be the angle whose sine is 2x, or arcsine of 2x is equal to theta. And that's using the definition of the inverse trig functions. So now we have 1 minus 4x squared dx is equal to 1/4 the angle whose sine gives you 2x. That's our theta, right? Now what about this second part? I've got plus 1/8 the sine of 2 theta. Well, you need a trig substitution for this one, or a trig identity for this one. This is one of the ones that I recommend that my students memorize because it comes up a lot. So the sine of 2 theta is equal to 2 sine of theta cosine of theta. So now I can replace this in the integral here, down here. So this becomes plus 1/8 times 2 sine of theta cosine of theta, and I still have my constant of integration. Now, what is the sine of theta? The sine of theta, I know what it is. It was my substitution factor. It's 2x. So I know what the sine of theta is, so I can now replace that in my expression for the value of the integral. So I have 1/4 arcsine of 2x. 2 divided by 8 is 1/4. And sine of theta is 2x. And what's the cosine of theta? Well, look at the triangle. The triangle will tell you the cosine is adjacent over hypotenuse. The hypotenuse is 1. So I just get the square root of 1 minus 4x squared. And then the constant of integration. Now, the last thing I could do, of course, is to simplify the 1/4 and the 2x. So I get 1/4 the angle whose sine is 2x plus 1/2 x, or x over 2, the square root of 1 minus 4x squared plus a constant. And that is the answer to this particular problem, right? So you can see how we ended up with different expressions that had to be evaluated using different techniques that we've learned so far. It's a long, involved process, and we're coming back to that basic substitution factor 3 times. One to build the pattern, a squared minus u squared, or u squared minus a squared, or a squared plus u squared. Once to replace the differential dx, and then again to get out of theta and back to the original independent variable of x using the right triangle picture. So now let's take a look at the next example, which has more than one piece in it. So when I'm looking at this particular problem, I've got the integral of x cubed over the square root of 2 minus x squared. So again, why would I even think to do trig substitution? Well, it's not a trig integral. It's all algebraic, so I'm not thinking integration by parts. So when I'm looking at this, the first thing I notice, I've got 2 minus x squared. Well, this x squared and this 2 minus x squared just kind of reeks of the Pythagorean identity. I can think of 2 as the square root of 2 quantity squared. So I'm thinking that this one must be a pattern of a squared minus u squared, a constant thing squared minus a variable thing squared. All right, so what do I want to do when I look at this and identify these pieces? I want to say a squared is equal to 2. So a is equal to the square root of 2, always picking the positive root. And then my u squared is going to be x squared. So my u is going to be x. So this is the simplest case. Simple not being simple at all, but simple for these. Now what do I need to do? I need to make my substitution. This reminds us of 1 minus sine squared of theta. So my substitution is going to be u equals a sine theta. So now I have u, which is x, equal to a square root of 2 sine of theta. Now I need to do two things with this. This is my basic substitution expression right here. This is the one that I'm going to be using 3 times. 1 to rebuild what's inside the integrand and to substitute out any other factors that are present. 2 to switch the differential from dx to d theta. And 3, after integrating, to get out of theta and back to x by using a picture of the right triangle and this expression to write it in terms of x. So I've got to use this 3 times. So the first thing I want to do is build this 2 minus x squared. So I start with 2 minus x squared, and then my x squared, of course, is my u squared. And then I've got 2 minus, well, what is x? It's the square root of 2 times sine of theta, and I square it. So this gives me 2 minus 2 sine squared of theta. Notice that the 2's become common factors. This is always going to happen. We're forcing a square peg in a round hole. We're building this pattern. This pattern will always occur. We take out the common factor of 2. That leaves us 1 minus sine squared of theta, which becomes cosine squared of theta. So we've gone from an expression in terms of x with 2 terms to an expression in terms of theta with 1 term. This is the first thing we use our substitution equation for. The second is to replace the differential dx. So now we want to come back to the original, and we have the derivative of x with respect to theta equal to the derivative with respect to theta of the square root of 2 sine of theta. Now, this gives me dx d theta on the left, and on the right, I have the square root of 2 as a constant factor, and the derivative of sine theta is cosine theta. Abuse the notation, swing the differential d theta around to the right, and I have something to replace the dx. So now I'm building it piece by piece to replace it. I've got something to replace 2 minus x squared. Under the radical, it's a single term, so I'll be able to take the square root. I have something to replace the differential. I'm feeling pretty good. Uh-oh, I've got an x cubed. Yikes. That wasn't in the previous example, but it's okay. I have an expression for what x is in terms of theta. So I can take x cubed and use this expression to replace the x cubed. So this is a third piece that we're going to have to use here. So we'll put this third piece in the middle. X cubed becomes the square root of 2 sine of theta, quantity cubed, which becomes 2 square roots of 2 sine cubed of theta. Now we have every piece that we need, and we're going to make our substitution now. So our original integral was x cubed over the square root of 2 minus x squared d theta, or dx. And then we're going to replace the x cubed with 2 square roots of 2 sine cubed of theta. Under the radical, I'm going to replace the 2 minus x squared with 2 cosine squared of theta. And then my differential dx is going to get replaced with root 2 cosine theta d theta. So I have the three different pieces that are getting replaced here. Everything that was in terms of x is now in terms of theta. Now, because of the way we define the angle, remember that the square root of cosine squared is absolute value of cosine. But because we're in quadrants 4 and 1, we know it's going to be positive no matter what. So this is going to, if I simplify it, give me a 2 square root of 2 sine cubed of theta times root 2 cosine of theta, d theta, over root 2 cosine of theta. Well, the cosine of thetas will cancel, and one of the root 2's will cancel the root 2 in the denominator, and that leaves me with 2 square root of 2 sine cubed of theta, d theta, which is a trig integral. So now you have to go back to one of the previous videos and work out how to evaluate that particular integral. So when we're looking at this one, we now have 2 square roots of 2, the integral of sine cubed of theta, d theta. Do you remember how to do the trig integrals? Pull 1 off of sine or cosine so that you're left with a multiple of 2 on the power. So that gives us sine squared of theta, sine theta, d theta. Now you're going to take the 2 and you're going to replace it with the Pythagorean identity, which is going to be, well, let's see, what would it be? 1 minus cosine squared. So this gives us 2 radical 2, the integral of 1 minus cosine squared of theta, sine theta, d theta. Now we do a u substitution, different u, not the same u as before, where u is cosine of theta, and du is equal to negative sine of theta d theta. So I need a negative to go in there. So sine theta d theta, which is what I have inside my integral, becomes negative du. I can put the negative in at the front, or I can use the negative to distribute over that 1 minus u squared to reverse the order. And this becomes 2 radical 2, the integral of u squared minus 1 du. Now, when we integrate that, we get backwards to 2 square roots of 2 times u squared. And when you integrate u squared, you get 1/3 u to the third, and u is cosine of theta, so we get cosine cubed of theta, minus 2 radical 2 of u, which is cosine of theta, plus a constant, right? Everybody with me so far? This is a very long, involved process. It takes multiple sheets of paper. Don't cramp up your work. It'll make you crazy. Now, this is great, but this is not a good answer for the left-hand side. The left-hand side right here is an expression in terms of x. So when we're looking at this in terms of x, I need an answer in terms of x, and I don't have that. I have an answer in terms of theta. So I'm trying to get back to the integral of x cubed over the square root of 2 minus x squared dx. And I got this expression that you see up there. Now, how can I get out of this? Well, I've got to go back to my original substitution equation. So let's go back up to our original substitution equation, which is way up here boxed up. X is root 2 sine of theta. So now we have x equals square root of 2 sine of theta. That's our substitution. This implies that the sine of theta then has to be x divided by the square root of 2. So we'll draw a right triangle with the angle theta in the lower left corner. Sine is opposite over hypotenuse. So we have x over radical 2. And then we'll use the Pythagorean identity to build the third side, which, no surprise, is going to turn out to be the square root of 2 minus x squared, which was the original denominator. No shock. Now, how can we rewrite this expression that came out to be in terms of theta in terms of x? Well, we've got to use this picture right here. So let's see, I can't quite get it all on there. So let me recopy what I have here so that we can see it all at once, hopefully. All right, well, I need to have the cosine cubed of theta written in terms of something with x, but I know what cosine of theta is going to be. It's going to be adjacent over hypotenuse, and I've got, well, I got to cube it. So basically, my integral for x cubed over the square root of 2 minus x squared dx is going to be 2 radical 2 over 3 times the expression, right? What cosine of theta is, radical 2 minus x squared, all divided by radical 2, cube that, and then minus 2 radical 2, and write cosine of theta again, which is radical 2 minus x squared divided by radical 2, and then plus c. Now I have returned the original answer into something related to x. Now I can do some simplification that I've got here with cubing things. So this is a square root, which is a 1/2 power. So I could write this to the 3/2 power. And if I cube the square root, I get 2 square root to 2. So I'll get a 1/3. So when I'm done with this particular one, I'm going to have basically the expression 2 minus x squared to the 3/2 power all over 3, right? Remember, the square root gives us the 1/2 power cubed, which gives us the 3/2 power. 3 square root to 2 is going to give us 2 square root to 2, so those cancel, and I still have the 1/3. And then over here, the square root to 2 cancel, and so I get minus 2 radical of 2 minus x squared, or you can write it to the 1/2 power, and then you've got your plus c. So you can see that these are quite long problems. They're really very tricky and complicated, but they're doable as long as you remember to keep going back to your substitution expression. Now, we've done 2 examples involving a squared minus u squared, where you have a constant type thing minus a variable type thing. So let's switch gears now and look at a different type. So there are 3 basic types: constant thing squared minus variable thing squared, constant thing squared plus variable thing squared, and the reverse, variable thing squared minus constant squared. So in the next one, we're going to be looking at the variable thing squared minus the constant thing squared. So similar, but in reverse order. Instead of a squared minus u squared, we have u squared minus a squared. So the variable is going to be in the positive term, and the constant is going to be in the negative part. But otherwise, it works very, very similarly, except that our substitution factor is going to be different. Because this has the variable on the left and the constant on the right, that gives us a different one that we want to substitute, namely a secant of theta. So we have u squared minus a squared, which reminds us of secant, oops, did I do that right? Secant squared of theta minus 1. So our u becomes a secant of theta. All right, so that's the factor that we're looking for right here, the substitution. So I look at the original, I try to identify the part that's calling for a trig substitution. It's this part under the radical. The x squared outside of it, I don't know how that's going to play out yet. It's just kind of sitting there for right now. Instead, it's this 4x squared minus 9. So what do we want to do with that square root of 4x squared minus 9? Well, we've got the variable thing first being positive minus 9. So we need to build our patterns. We identify the pieces, and it looks to me like u squared is equal to 4x squared. Take the square root of each part, make it be the positive root. So u is 2x. And a squared is only the constant, 9. So a is equal to 3. So now I'm going to build my substitution factor. And I'm going to come over here and I'm going to say that u is equal to a secant of theta. It's always going to be a times one of the trig functions. All right. So when we're looking at this one, my u is 2x, my a is 3, and I get secant of theta. So I have 2x equals 3 secant of theta. So you see now that u is not just x, it's a function involving x, right? Now what do I need to do? I need to rebuild the 4x squared minus 9 and switch it from being in terms of x to being in terms of theta. And then I need to switch the differential from dx to d theta. And then I'll have to substitute out this x squared. Okay, so how do I do that? One piece at a time. First things first, let's switch the 4x squared minus 9. So I'm going to come over here to the left, and I'm going to write 4x squared minus 9 equals. Well, 4x squared is the same thing as 2x being squared minus 9. But 2x is 3 secant of theta, so I can replace the 2x with 3 secant of theta. Now what do I want to do? Well, I'm going to square that to get 9 secant squared of theta minus 9. Factor out the 9. I get secant squared of theta minus 1, which is what I was supposed to get, right? That's what it reminds me of. And I can replace that with tangent squared. So now I have replaced something that was 2 terms in terms of x into something that's 1 term in relation to the independent variable of theta. Now, the next piece that I want to do is I want to replace the differential. So I'm going to replace the differential as my next step, and I'm going to outline my basic substitution. So I'm going to take the derivative with respect to theta of 2x, and then I'm going to take the derivative with respect to theta of 3 secant of theta. Well, the derivative of secant of theta is 3 secant theta tangent theta. And the derivative of 2x with respect to theta is 2 dx d theta. Abuse the notation and swing the d theta around, and at the same time swing that 2 into the denominator. So I get 3 halves secant of theta tangent of theta d theta. That is going to replace my differential dx. So now, if I'm looking at this problem, I've replaced the 4x squared minus 9. I've replaced the differential. Now I've got this x squared. How am I going to replace x squared? We'll come back to your substitution. I can solve for x by dividing both sides by 2. So I could say that x is equal to 3 halves the secant of theta. And if that's the case, then I can just square it. And that would give me that x squared is equal to 9 over 4 secant squared of theta. And that gives me something for each piece of the original integrand. And I can now replace it as well as the differential. So now we're going to replace our original integral with something in terms of theta instead. So I have the integral of dx over x squared, square root of 4x squared minus 9 equal to, dx is going to be replaced with 3 halves secant theta tangent theta with a d theta divided by, and then x squared becomes 9 over 4 secant squared of theta. And then I've got this square root of 9 tangent squared of theta. Okay, so hopefully you followed all of those pieces. And now we need to do a little bit of simplification. So when we do our simplification here, 3 halves divided by 9/4, the 3 over the 9 becomes 1/3. The 4 is the denominator of the denominator, so it flips to the numerator. 4 over 2 gives me 2, so I get 2/3. So I'm going to pull the 2/3 out of the integral. So this is going to give me a 2/3. One of these secants will cancel one of these secants, and that will leave me a secant in the denominator. So then I'm going to have secant of theta in the denominator. And then I've got this square root of 9 tangent squared. This is the one that causes us problems. Unfortunately, we don't know whether x was greater than or equal to c or less than equal to negative c because it's not a definite integral, so we can't evaluate that. So we're just going to have to assume it's the positive one. That's what most textbooks do, but do be aware that it is a slight problem on definite integrals. So we get 3 tangent of theta. In other words, the absolute value of tangent of theta here isn't always tangent of theta. It could be negative tangent of theta. So at worst, you'd be off by negative. Okay? Now what do we do? Well, I also have a tangent of theta in the numerator. And I've got d theta. So my tangent of thetas cancel. And I've got this 3. So this is going to become a 2/9. Now, this 1 over the secant of theta, the reciprocal of secant, of course, is cosine. So this gives me 2/9, the integral of cosine of theta d theta. Well, that's about as easy as it gets these days. So that just becomes 2/9 sine theta plus c. Now, remember, we started with an integral in terms of x. We converted the integrand into something in terms of theta, converted the differential dx into something in terms of d theta. We integrated, got an answer in terms of theta, which we now have to revert back to x. So now we're going to go back to our substitution expression, 2x equals 3 secant of theta. And we're going to draw a right triangle that expresses the trig function. So this means secant of theta is equal to 2x over 3. Drawing our right triangle, remember that secant is hypotenuse over adjacent. So this becomes 2x, and this becomes 3. And this third side then becomes 2x squared, which is 4x squared, minus 3 squared, which is 9. Which, no surprise, this gives us the same expression we started with here. Now we need to rewrite this answer that we have right here in terms of x instead of in terms of theta. So looking at the triangle, we can see that the sine of the angle is the radical of 4x squared minus 9, all divided by 2x. So now I can come down here. This becomes 2/9 times, replace sine of x with square root of 4x squared minus 9 divided by 2x plus c. The 2's cancel, and I get the square root of 4x squared minus 9, all divided by 9x plus a constant. And that's my final answer, all right? So it's back in terms of x, so I know that it is an appropriate answer for this particular integral. It took a lot of work. I had to use this substitution equation 3 times. Once to change each part of the integrand into something I could substitute in terms of theta, once to convert the differential dx to d theta, and the third time to get out of the value of the integral in terms of theta back to an answer in terms of x. Let's look at another one of these examples of u squared minus a squared. So here's another example of a u squared minus a squared type trig substitution problem. So how do I know that it's u squared minus a squared? Well, I've got a variable thing squared minus constant. This constant happens to be 9 again. I guess I was stuck on 9 when I was writing this up. And then it's got an x down here, but don't freak out. We'll be able to replace each piece. So again, this reminds us of u squared minus a squared, where a squared is always the constant part. So this means that my u is going to be, or u squared is going to be x squared. So u is equal to x. and a squared is 9, so a is equal to 3. This reminds us of secant squared of theta minus 1. So our substitution is going to be a secant of theta. All right, so u is x, so we have x equals 3 secant of theta. Now we need to do something here to change what's under the radical to be an expression of theta. We need to change the x to be an expression of theta, and then we'll have to take the derivative of this original substitution equation in order to change the differential from dx to d theta. So let's tackle each piece independently. So we want to rebuild x squared minus 9. So x squared becomes 3 secant of theta squared minus 9, which becomes 9 secant squared of theta minus 9, which is 9 secant squared of theta minus 1, which is 9 tangent squared of theta. Again, going from 2 terms in terms of x to 1 term in terms of theta. The next thing we want to do is we want to substitute out the differential, which is the dx. So we're going to take our substitution equation and take the derivative of both sides of it with respect to theta. So we have the derivative with respect to theta of x and the derivative with respect to theta of 3 secant of theta. So this is going to give me dx d theta, which is equal to 3 secant theta tangent theta. The right side is a function of theta, so I don't have the differential left. Then abuse the notation and swing the d theta around to the other side. So we have an expression to replace the differential of dx. Now we have something to replace what's under the radical. We have something to replace the differential. The only thing we need left is to replace the x, but I already have an expression to replace the x, so I don't actually have to do anything extra here. It's ready to go. So now I have the integral of x squared minus 9 under the radical divided by x. So this becomes the integral of the square root of 9 tangent squared of theta. And again, we would normally need to worry about whether the absolute value of tangent was tangent or negative tangent, but without knowing where the x is being evaluated, we can't determine that. If x is greater than or equal to c, it's positive. If x is less than or equal to c, it's negative, but we would need a definite integral to know that. So then in the denominator, our x becomes our substitution factor of 3 secant of theta that you see here. And then our dx, we can borrow from up above, is 3 secant of theta tangent of theta d theta. Now the secant of theta cancels and the 3 cancels. And since it's an indefinite integral, we'll just have to assume that it turns out to be a positive tangent of theta. And so then we have 3 tangent of theta times tangent of theta d theta, which gives us 3 tangent squared of theta d theta. Now, you're looking at that one and you're going, how do I do that? Back to trig integrals again. So this is a trig integral because it's got trig in the integrand. So we're looking at it and we're like, oh, I've got 2 of them. If I've got 2, I can use that Pythagorean identity to substitute it out. Well, I don't see that I have anything to serve as part of du, but maybe I don't need a u substitution. I don't really have a choice. I don't have anything else I can try. So I'm going to try substituting tangent squared of theta with secant squared of theta minus 1 d theta. Split it into 2 integrals. And now you have the integral of 3 secant squared of theta d theta, which of course integrates directly because the antiderivative of secant squared is tangent. And the second one also integrates directly because the antiderivative of 1 is just theta. So this gives me 3 tangent of theta minus 3 theta plus a constant. Okay, well, that looks pretty good. I think I'm happy with that, except that my original integral was in terms of x. So I've got to use that substitution factor again for the third time in order to get back into terms of x. So we're going to write it down again, and maybe I'll use a different color this time to make it stand out. X equals 3 secant of theta. And now I'm going to draw my triangle. They're getting smaller and smaller. I don't know why. Remember that this is my substitution equation. And so secant of theta is equal to x over 3. Secant is going to be hypotenuse over adjacent. So this becomes x over 3. So this side becomes x squared minus 9. Now, theta is going to be the arc secant of x over 3, right? Remember, to solve this for theta, you have to take the inverse trig function of both sides. So this gives me the angle whose secant is x over 3 is theta. And that will replace the theta. So coming up here now, I have 3 tangent of theta. Tangent is going to be opposite over adjacent. So I have x squared minus 9 over 3. So the 3 should cancel. And then I have minus 3, the angle whose secant gives me x over 3 plus a constant. And then I can simplify and cancel the 3's. And I end up with the radical of x squared minus 9 minus 3 arc secant of x over 3 plus a constant. And that's my final answer. Now we have one more type that we want to take a look at. We've looked at having a constant thing squared minus variable thing squared. And we've looked at the variable thing squared minus the constant thing squared. The only thing we haven't done is what if there's no minus, right? What if they're both positive? So that's our last possibility. So let's take a look now at integrals involving a squared plus u squared. For our last type, we're looking at these ones which are constant thing squared plus a variable thing squared. These are the ones that are most likely not to be under a radical. The other two tend to be under radicals most of the time. I won't say always. I'm always hesitant to say always. Not too many times you can say always in mathematics. But most of the time, the first two, where one of them is negative, tend to be under radicals. This one may or it may not, all right? So in our first example, it is under a radical. And in the second example of this type, we'll see it's not under a radical. So when we're looking at this one, what leads us to this trig substitution pattern? Well, I've got a 5, which is a constant, which I can always think of it as square root of 5 quantity squared, plus a variable thing squared. So I chose something relatively simple for our first example. So when we see this constant plus variable thing squared, we tend to think in terms of 1 plus tangent squared. So when we do 1 plus tangent squared, we're going to make a substitution of u equal to a tangent of theta. So this is going to be that middle case that we talked about at the very beginning of the video. So this is the middle case, not the more complicated one where sometimes the absolute value of tangent is positive and sometimes it's negative. This one is going to give us secant. And because we define the angle for this one to be in quadrant 4 or 1, secant's positive in both. So we always get positive secant of theta. So we don't have to worry about taking the radical here. It's not going to be an issue. So what do we want to do on this one? Well, I want to identify the different pieces. So I have a squared equals 5. So a is the square root of 5. And then I've got u squared equals x squared. So u is equal to x. So then I'm going to do my substitution, which is that u is equal to a tangent of theta. U is x. So I get square root of 5 tangent of theta. This is my substitution factor. All right, so this is what I'm going to be using the three main times in order to go back and forth. So now I've got to convert and find what is going to replace the 5 plus x squared under the radical. Then I'll have to find what replaces the dx, and I'll have to find something to replace the x squared. These will all have to be written in terms of theta instead, and we hope that what goes under the radical gets reduced from 2 terms to 1, so we can easily take the square root of it. So first things first, I'm going to go ahead and rebuild what was underneath of the radical. So I'm going to rebuild this 5 plus x squared. Well, this becomes 5 plus the square root of 5 times tangent of theta, quantity squared, which is 5 plus 5 tangent squared. 5 becomes a common factor, which you take out, and that leaves you with 1 plus tangent squared of theta, which gets replaced with secant squared of theta. So I've gone from something in terms of x to something in terms of theta, and from 2 terms to 1 term. So now when I replace what's under the radical with this, I'll be able to take the square root of it, and the absolute value of secant of theta, because of the way I define theta, will just be positive secant of theta. This is the first one. Now I also have to use that expression for the basic substitution to find the differential. So I got to replace the differential. So I take the derivative of both sides of that equation with respect to theta, and then I'm going to work out what dx is by abusing the notation and swinging the d theta over to the right side. So this gives me dx d theta on the left equal to square root of 5 secant squared of theta. Now, again, the derivative of tangent of theta is secant squared of theta with respect to theta, so there's no differential left on the right side. Abuse the notation and swing that d theta around. So I have dx is equal to radical 5 secant squared of theta d theta. Theta didn't quite form there. Okay, now that lets me replace what's under the radical and the differential. What's left is this x squared. Well, I have an expression for x, so I can just square it, and that will replace that factor. So we're replacing each piece as we go. So this becomes the square root of 5 tangent of theta, quantity squared, which becomes 5 tangent squared of theta. Now we're going to replace each piece in the original integral so that we can integrate with respect to theta instead of integrating with respect to x. So we've turned it from an algebraic integral in terms of x into a trig integral in terms of theta. So my x squared becomes 5 tangent squared of theta. My denominator becomes the square root of 5 secant squared of theta. And my differential dx becomes radical 5 secant squared of theta d theta. Now, I need to simplify this one a little bit. I'm going to be doing some basic algebra here. Remember that really, when we do this one on the bottom, we get radical 5 absolute value of secant of theta, not secant theta. But because of the way I defined the angle to be only in quadrants 4 and 1, secant's positive in both of those, so I can drop the absolute values. So this is going to give me a secant of theta in the denominator and a secant squared in the numerator. And the square roots of 5s will cancel, and one of the secants will cancel. So I still have a 5, I still have a tangent squared of theta, and I still have a secant of theta d theta. Okay, does this ring a bell with anybody? This is back to a trig integral again. I know you're like, oh my God, this is so complicated. It is complicated. Calculus is complicated, and calculus 2 is the most complicated part of a complicated system. Cal 3 is less complicated than Cal 2. I know you don't believe me, but it really is. It's less complicated. So now when we're looking at this one over here, we have a bit of an issue. So how are we going to convert this one? What are we going to do here? Well, the problem is secant of theta by itself is not the derivative of anything. So I can't use the secant theta d theta to become part of du. It's just not going to work. It's either got to be secant theta tangent theta, or it's got to be secant squared of theta, which means my only option is to convert this tangent squared of theta into something in terms of secant of theta. Now I'm going to leave you to do that at home. I'll write out the steps and then I'll scroll through it slowly so you can see it. But I'm not going to go through that here because it is, again, a trig integral. And we went through this exact example in that video. So go ahead and pause the video, work it out, and turn it back on and compare your answer to mine. So how long did it take you? 30 minutes? An hour? I'm sorry. I know it's a nightmare. So we're looking at this problem. We started here with the integral of x squared over square root of 5 plus x squared times the differential dx. We substituted each piece out for something in terms of theta. Then we integrated what was left. So here is our integral in terms of theta. Now we want to integrate this in terms of theta, but we need to do a trig integral to do that. So we replace tangent squared with secant squared of theta minus 1, which when we split it into two integrals, gives us 5 the integral of secant cubed of theta minus 5 the integral of secant of theta. Now these both integrate in different ways. The pink one is the easier one. There's a trick where you multiply, or a technique, by secant plus tangent divided by itself. And that's just a form of 1. And it leads to a u substitution where u is the denominator and du is actually exactly the numerator. So you get the integral of 1 over u du, which is the natural log of the absolute value of u, which was the denominator. So this one's not too bad. The secant cubed, it's bad, all right? I'm sorry, it's just, I mean, how awful can this be? You've now learned every technique that you've learned this semester, you're having to use in this one problem, right? Plus a bunch you learned in Cal 1. So in order to integrate secant cubed, you need integration by parts. So you pull off 2 of them to serve as dv, and the single one becomes u. So you let u be 5 secant of theta. So the derivative is 5 secant theta tangent theta. And then you integrate the dv side to lead you to tangent of theta. Remember that we choose that constant to be 0 when we're doing integration by parts. Then we get u times v, 5 secant theta tangent theta, minus the integral of v du, minus 5 the integral tangent squared of theta, secant of theta d theta. So let's put it back together again. I started with this. It's equal to this, which is equal to these two, which is now equal to this minus this minus this, plus constant of integration. Now, this is where it gets really tricky. These two are multiples of each other, right? This one's 5 times the integral. This is negative 5 times the integral. They're multiples. We got to get those two terms together. But the problem is the original integral that I started with that had x in it, that's not equal to 10 of those. Up here, it's equal to 5 of those. So when I get 10 of them, I've got double what I need. I need 5 of them, and now I've got 10. So I'm going to divide by 2, right? Which is basically the next thing I do. So I move this one from the right side to the left side, which gives me 10 of them. And that leaves 5 secant theta tangent theta minus 5 natural log absolute value of secant plus tangent plus the constant of integration. Now that's 10 of those integrals, which is double the one I started with. So which was 5 of those. So I just divide the right side by 2, and then I have my value for the integral in terms of theta. We are still not done. I'm sorry. These just go on for pages and pages. So you may be on page 3 now, but you will be happy to know that this is as bad as it gets, all right? These are the worst of the worst. I mean, we had to use every technique here. So this is everything and the kitchen sink, right? So now we've got to get out of theta and we've got to get back to x. So we use our substitution equation again, back from the original, and I'm going to box it up, and maybe I need to use the same color. So I have x equals square root of 5 tangent of theta, and I'm going to draw my triangle. So I've got my triangle over here, right angle, theta. Now, this basically implies that the tangent of the angle is x divided by the square root of 5, just solving for tangent of theta by dividing both sides by root 5. Well, tangent is opposite over adjacent. So the opposite of theta is going to be x. So that's this side, right? Remember, you're shooting an arrow out of the angle. This is opposite. This is adjacent or attached, but not the hypotenuse. The hypotenuse is also attached, but it's the hypotenuse. So this becomes square root of 5 down here on the bottom leg. The legs are the short sides. And then I can build the long side, the hypotenuse side, by using the Pythagorean theorem. It's got to be the square root of this side squared plus that side squared. If I square the square root of 5, I get 5. And if I square x, I get x squared. No surprise, we get the same expression that we had up here in the original integral. So this should happen. If you've done it correctly, this should match this up here when you're looking for that third side. Now, coming over here, I've got this expression right here, which is the one I need to replace. So let me highlight this one over here in another color. This right here. This is what I need to get back into terms of x. So when I'm looking at this one, what I want to say then is that the integral of x squared over the square root of 5 plus x squared with differential dx, which was 5 of that trig integral tangent squared theta secant of theta d theta, becomes 5/2 secant theta times tangent of theta. Okay, replacing each piece. We're doing substitution like on steroids here, right? Substitute, substitute, substitute. What is secant of the angle? Stare at the triangle. Secant is hypotenuse over adjacent. So square root of 5 plus x squared over square root of 5. Square root of 5 plus x squared over square root of 5. That replaces secant of theta. What about tangent of theta? Opposite over adjacent, x over the square root of 5. Minus 5/2, natural log, absolute value, secant theta again, which was that first expression, 5 plus x squared under the radical divided by radical 5, plus tangent of theta, which was the second expression, x over radical 5, plus a constant. Now, can you clean this up? Yeah, you can clean it up a little bit. In fact, there's some really tricky algebra going on here. In some of your textbooks in the solutions manual, you're going to sneak this really sneaky algebra in here. So let me show you how it goes so that you don't freak out when your answer, which is this, doesn't look at all like the answer in the back of the book. Okay, so when you're looking at this, notice I've got radical 5 and radical 5 in the denominator. So those two give me a 5. It cancels that 5. So I've got an x over 2 times the square root of 5 plus x squared. So x over 2 times the square root of 5 plus x squared. That algebra, that's okay. I mean, it's not fun. I mean, but compared to what we've been doing, piece of cake at this point. All right, now what about this back part? Okay, here's where it gets really tricky. It looks at this and it goes, well, hey, these guys have a common denominator, right? Okay, you see where I'm going? Yeah, so this is what some textbooks will do. Very, very sneaky. They're going to have this minus 5/2 natural log, and they're going to write the square root of 5 plus x squared plus x in the numerator and the square root of 5 in the denominator. It's still not going to be what's in the back of the book. Now, you know from algebra, college algebra or pre-calculus, long time ago at this point, that when you have the natural log of two things and they're being divided, that it's the natural log of the numerator minus the natural log of the denominator. So they're going to split it into two natural logs. I can see you rolling your eyes. Get those eyes back facing forward so you don't get lost. Now we have minus 5/2, and I'm going to use big parentheses. They're going to have the natural log of the absolute value of the square root of 5 plus x squared. That's where my variable is, where I need the absolute values. Now, the absolute value of square root of 5 is square root of 5, so I can drop those. And it gives me minus the natural log of the square root of 5 plus a constant. Now, this is the tricky piece. Negative 5 halves gets to multiply by both of these things. There are two terms in there. Two. Here's term 1. Here's term 2. Two things split up by that minus that's out in the open. These guys don't count. They're inside the absolute value. They're buried. Okay, negative 5 halves times the negative natural log of the square root of 5 is a constant. Let me say that again. When I distribute across the second term, negative 5 halves times negative natural log of the square root of 5, there's no variable there. It's just a constant. They're going to take that constant and they're going to roll it into C. So let me take 2 steps to write it out so I don't lose some of you, because at this point you're probably a little bit brain dead and pretty tired, and we still have one example to go. So we have minus 5 halves natural log of the absolute value of square root of 5 plus x squared. Oops, that didn't look good. My plus looked like an x. Plus x plus 5 halves natural log of the square root of 5 plus c. What you're going to see in the back of the book is probably going to be this. They're going to take both of those terms at the back and roll them all together into one big plus c. All right? Does that make sense to everyone? I hope you're following the algebra here. Algebra really is the key to doing calculus well. If your algebra skills are weak, your calculus is necessarily going to be weak. All right? It's the foundation on which we build. Let's take a look at the last example, which you'll be happy to know is not the hardest one in this set. We've already done the most difficult ones. That was this one and the one that involved the integration by parts. So this was a hard one, and the one before it, I believe, was the other hard one. So we have one more example to do, which is example 6. I left myself a lot of space there. Okay. So looking at this one, you may go, oh, that doesn't look like the Pythagorean theorem. And you'd be right. It does not. This does not look like the others. We're trying to match patterns. Whatever our pattern's been, our patterns have been a squared minus u squared, or u squared minus a squared, or what we've been doing lately, a squared plus u squared. It doesn't look like any one of those. For one thing, it's got 3 terms. That's not something squared plus something else squared. But I can shove that square peg in a round hole if I want to, because I can make it into something squared plus something else. And how do I do that? I complete the square on it. This is back to algebra again, so we're going to complete the square. Notice that this one doesn't have a radical at all, right? Maybe it does, maybe it doesn't, but this one doesn't. So how am I going to solve this problem? I'm going to take this problem and I'm going to rewrite it by completing the square on the 2x squared plus 4x plus 7. So this is a technique that we use to solve quadratic equations. Remember, we can use the quadratic formula or we can complete the square. Both of those techniques work all the time, right? They never fail, and that's why it's important to know them both. Now, in order to complete the square on the 2x squared plus 4x plus 7, I like to have a lot of space, all right? The more cramped it is, the harder it is for me to keep track. So the first thing I do is I have 2x squared plus 4x, and I'm shoving that 7 out of the way. Move over, all right? I need space. These are the 2 on which I'm going to complete the square. They're going to form my first something squared, and the constants that get over here are going to form the second something squared, all right? They may not be perfect squares, but I can take the square root of it and square it, and that makes it a perfect square. Okay, so what's A and what's B? We've got A is 2, B is 4, C is 7. We don't care about C. We care about A and B. So when I'm looking at A and B here, and this is coming from the quadratic formula, A is 2 and B is 4. And I'm going to form 1/2 of B over A. All right, this is from completing the square, which I hope you remember, but maybe you don't. And if you don't, this is a good review. So we have 1/2 of 4 over 2. 4 over 2 is 2. So I have 1/2 of 2. All right, I have 1/2 of 2, which gives me 1. All right, so half of B over A is a 1. The next thing I want to do is I want to square it. All right, so I'm going to take this half of B over A and I'm going to square it. In this case, it doesn't change it. 1 squared is still 1. Now what do I want to do? I need to come up here to this original expression, and I need to force that coefficient of x squared to be a positive 1 by factoring A off of these two terms. So I'm going to switch colors here so that you can compare and contrast. So I'm going to take the 2 off the x squared and the 4x to give me x squared plus, or the 2x squared and the 4x to give me x squared plus 2x. And my plus 7 is shoved over out of the way, all right? So I factor off the leading coefficient, which gives me a 2. I've built what I needed to do the completing of the square. I take this half of B over A and I square it, and that gives me a plus 1. This plus 1 has to come in here, but it was not originally in the problem. So far, this is equivalent to the original, right? I haven't changed it yet. Now I'm going to do something that changes it. So I'm going to add 1 in here, and then I'm going to factor that part, right? But I've now changed the problem because I added 1 that wasn't there. So to compensate, I subtract 1, right? So I've added 0. This is called adding 0. So you add a number and subtract the number. What have you added? Nothing. Okay. The first 3 terms factor as a perfect square trinomial. It becomes a binomial squared. If you don't believe me, test it out. It is always going to factor as x plus 1 quantity squared. That number is going to be right there every single time, right? No exceptions, right? We're forcing it to fit a pattern. Now, what about this minus 1? Well, it's inside parentheses. It should be multiplied by the 2. So I really have 2 times minus 1, or a minus 2. This is the part that wasn't originally in there. And then I still have my plus 7. Do you see where I'm going with this? I started with 3 terms, 2x squared plus 4x plus 7. And now I've got 2 times the quantity x plus 1 squared, which is 1 term. And I've got 2 constants. But I can combine the constants. And this is then going to lead to 2 terms instead of 3 terms. So this is a term, and this is a term. So I'm going to take my original integral, which is right here, and I'm going to rewrite it in terms of this completed square expression. So I have the differential over 2x squared plus 4x plus 7 must be equivalent to the differential divided by 2 times x plus 1 quantity squared plus 5. So I've gone from 3 terms here in the denominator to 2 terms. Now it does look like something that I can use that Pythagorean pattern on, something squared with the variable and a constant. Yes, I've got a 2 here, so I'm going to have to use a square root of 2. So when we're looking at this particular one, let's start pulling apart the pieces that we now have. So we're going to build for this one. We have a squared plus u squared, or u squared plus a squared, whichever way you want to write it. So our a squared, maybe we should write it the other way since that's the order that it's in this time. Remember, a is always the constant and u is the thing that has x in it. So our a squared is 5, and our a is the square root of 5. Our u squared is the other term, 2 expression x plus 1 quantity squared. So u must be the square root of 2 times x plus 1, the quantity. All right. Okay, so far so good. That seems to match the pattern. What do I do? Oh yeah, I need to make a substitution. So the substitution I'm going to make is the one with tangent, because this reminds us of tangent squared plus 1. So I'm going to do the substitution, u equals a tangent of theta. Now, how do I keep them straight? Here's the trick that I use. If it has a minus in it, it's not tangent, because tangent starts with the letter T, which looks like a plus sign. Tangent is the one with the plus sign in it. 1 minus the variable thing is always sine. And when the variable thing comes first and then it's minus the constant, that's secant. So I keep those in order that way. So tangent I always associate with the plus sign, and that's how I do it. So now I need to make my substitution. So I've got radical 2 times x plus 1 is equal to a square root of 5 times tangent of theta. This is my substitution equation that I'm going to be using multiple times in order to convert the original integrand into something that can be integrated by converting it into an integrand in terms of theta, and then getting back out of that using the right triangle trigonometry. So the first thing I want to do is I want to rebuild this denominator that I have here in the bottom. And I've got this square root of 2 times x plus 1 quantity squared, which becomes radical 5 tangent of theta. So coming up here, I'm building what I have. So I have 2x plus 1 squared plus 5, which is going to be equal to the square root of 5 tangent of theta squared plus 5, which gives me 5 tangent squared of theta plus 5. Factor out the 5, you get tangent squared of theta plus 1, which leads to secant squared of theta. So now I've gone from 3 terms to 2 terms to 1 term. And I've gone from something in terms of x to something in terms of theta. Now I need to take the derivative of this side, and I want to take the derivative with respect to theta. Now notice it's got x inside parentheses. So if I want to, I can clean it up a little bit first before I do that. So coming over here, I might instead write the square root of 2x plus the square root of 2 equals the square root of 5 tangent of theta. Then I want to take the derivative of the left with respect to theta and the derivative of the right with respect to theta. Right? So I've got the 2 different sides. I'm going to take the derivative with respect to theta. Radical 2 is a constant, so it pulls through. So I get dx d theta from the first term. Now the second term, square root of 2, it's a constant. The derivative of a constant is 0, so it's gone. And then the derivative of the right side, the radical 5 is a constant, so it pulls through. And the derivative of tangent of theta with respect to theta is secant squared of theta. So we get radical 5 secant squared of theta. Okay. Now the next thing that we want to do, and I've lost something. What did I lose? I lost my radical 2, which should have come to the front. Then we abuse the notation. We divide both sides by d theta, and we divide both sides by radical 2. So this gives me that dx is equal to radical 5 divided by radical 2, or you can write it as 1 radical, secant squared of theta, d theta. And now I have the 2 pieces I need to replace the original integral. So coming up here to the original integral, we had the integral of 2x squared plus 4x plus 7, which we rewrote as the integral of 2 times x plus 1 squared plus 5 And now we can replace that with the integral of 5 secant squared of theta, replacing the denominator, and dx being replaced by radical 5 over radical 2 secant squared of theta d theta. What happens to those secant squareds of theta? Well, they cancel, right? So they cancel and they disappear. And I've got a radical 5 on top and a radical and a 5 in the denominator, which will give me 1 over radical 5. I've also got a 1 over radical 2, so I'll be able to combine those two. So this is going to give me basically, if I write it out, 1 over radical 2 is 1 over radical 5, just d theta. That's it. That's all that's left. You should be celebrating. So 1 over radical 2 times 1 over radical 5 is 1 over radical of 10, and it's going to be theta plus a constant. And then you may say, well, what does that turn out to be? We'll come back up here to your substitution value. In this case, we don't even need the right triangle, but we can write it. It won't hurt us. We have radical 2 of x plus 1 equal to square root of 5 tangent of theta. This is our substitution equation that we've used multiple times to convert from an integrand in terms of x to one in terms of theta, from a differential dx to a differential with d theta. And now we need to go backwards. We need to use this again, solve for the trig function, which is tangent of theta. So tangent of theta is equal to radical 2 times x plus 1, all divided by radical 5. So theta must be the angle whose tangent is this expression right here. And that's all we need to finish our problem. So this part right here becomes 1 over radical 10 times the arctangent of 2x plus 1 over radical 5 plus a constant. And that's our final answer. Now, could you simplify it a little bit? No, not really. You really can't. There's not anything you can do. All of this is inside the arctangent, so hands off the argument to arctangent. And that's really the only thing you can do is just leave it like this, and that's good enough, right? So we've done this trig substitution process 6 times now, where we saw 3 basic patterns: a squared minus u squared minus a squared, and u squared plus a squared. In all cases, we were using something like the Pythagorean identities to replace things using trig substitution. We used that factor multiple times, and then we used the right triangle to go backwards to get out of theta and back to x. I hope that this makes sense to you and that you've enjoyed some of learning about this. These are some of my favorite problems to do, even though they're quite complicated. And I hope that you will join me in the next video, where we'll probably be looking at partial fractions, yet another integration technique.